The very foundations of modern science came within a whisper of vanishing forever. This is the untold story of the monastic translation centers that saved classical mathematics from complete erasure. By the end, you will understand exactly how a fragile network of scribes and scholars across deserts and mountains preserved the intellectual toolkit that built our world. We will uncover why certain brilliant works disappeared into the shadows of history while others survived, and how the quiet act of copying a book in a cold stone room could alter the destiny of human thought. What does it truly take to keep an idea alive for 1,000 years? The Roman roads fell silent, not with a bang, but with a slow, deep quiet. Imagine the intricate network that once pulsed with imperial messengers, merchants, and marching legions gradually growing still. This silence was more than just an absence of sound. It was the sound of a system breaking down, the vast administrative machine that had, for centuries, curated and copied texts, funded scholars, and connected thinkers from Spain to Syria, simply ground to a halt. In Western Europe, the unified scholarly world of the Mediterranean fractured into isolated pockets. The common language of advanced learning, Greek, began to fade from memory in the West, becoming a distant, almost magical script few could decipher. This created a profound disconnect. The most sophisticated works of mathematics, written in Greek, became locked away in a language barrier as formidable as any castle wall. The very material of knowledge was fragile. Classical works were preserved on papyrus scrolls, a medium derived from a water reed. While excellent in the dry climate of Egypt, papyrus did not fare well in the damp, cool climates of northern Europe. It grew brittle, moldy, and could simply crumble to dust within a generation or two if not meticulously recopied. And who was left to do that copying? In a world where day-to-day survival became the overwhelming focus, the abstract beauty of a geometric proof or an algebraic equation seemed like a distant luxury. As historian James Hannam notes, mathematics was particularly vulnerable. It wasn't seen as immediately vital for salvation like theology, or as necessary for governing a fractured kingdom like law. It was the first layer of knowledge to be stripped away when times grew hard. This was not a sudden, dramatic burning of a library, though those tragedies happened too. This was something slower and in many ways more complete. It was a fading, complex concepts built over generations of thought began to slip from collective memory. The meticulous logic of Euclid's elements, the astronomical calculations of Ptolemy, the number theory of Diophantus, these weren't actively destroyed. They were simply no longer taught, no longer copied, no longer understood. One by one, the lamps of knowledge were going out across the landscape, creating a gathering darkness and a vacuum of understanding that would stretch on for centuries. The question was not just what had been lost, but whether anything of that brilliant legacy could possibly survive the long night ahead. Yet to the east, a different kind of flame was being kindled. As the long night settled over Europe, the newly established Abbasid Caliphate was entering a golden age of its own, fueled not by isolation but by a voracious cosmopolitan curiosity. Its capital, Baghdad, founded in the 8th century, was designed as a circular city of peace, a grand intellectual crossroads at the very center of the known world. Here, the ruling caliphs pursued knowledge with the same strategic ambition as territory. The most famous of these patrons was Caliph al-Ma'mun, a ruler who reportedly dreamed of the ancient philosopher Aristotle, compelling him to seek out and preserve all the wisdom of the ages. From this vision arose the Beit al-Hikmah, the House of Wisdom. This was no silent scriptorium. Imagine a bustling, state-funded academy that combined the functions of a library, a translation bureau, and a research institute. It was a hive of scholarly activity where Christian, Jewish, Muslim, and Zoroastrian thinkers worked side by side, united by a common language of inquiry, Arabic. The project was systematic and lavishly supported. Teams of scholars were sent on expeditions to acquire every scientific and philosophical manuscript they could find, from the Byzantine Empire to the distant monasteries of Syria and Mesopotamia. Translators like the famed Hunayn ibn Ishaq were compensated with astonishing generosity, sometimes paid their weight in gold for the works they rendered into Arabic. This created an unprecedented repository. Within the House of Wisdom, the endangered Greek legacy of Euclid, Archimedes, and Ptolemy met the sophisticated astronomical models of Persia and the revolutionary numerical system from India, which included the profound concept of zero. But this center did far more than just collect and copy. It acted as a crucible for innovation. Here we meet the Persian scholar Muhammad ibn Musa al-Khwarizmi. Working under the caliph's patronage, he didn't merely translate Greek texts. He synthesized them with other traditions to write foundational works that gave us the words algebra from his book Al-Jabr and Algorithm, a Latinization of his own name. Meanwhile, the Banu Musa brothers, three wealthy scholars, funded a massive translation campaign and themselves authored ingenious works on geometry and mechanics. This was the critical difference. In Baghdad, the torch of classical learning was not hidden away in a cellar for safekeeping. It was brought out into the open square, its flame used to ignite new fires. The knowledge was actively debated, corrected, expanded, and built upon. Greek geometry was fused with Indian numerals to create new forms of calculation. Persian star charts were refined with Greek observational methods. The result was a new, vibrant, and more powerful body of knowledge, written in Arabic, that would eventually make its way back to a Europe just beginning to stir from its long intellectual sleep. The question now was not if the knowledge would survive, but how it would ever find its way home. The journey of a single page from Alexandria to Baghdad was a relay race across languages, faiths, and empires. It rarely happened in one dramatic leap. More often, it was a careful two-step process, and its first, crucial translators were not Muslim or Arab, but Syriac-speaking Christian scholars. For centuries, these communities had thrived in the borderlands between the Byzantine and Persian Sasanian empires. They were the inheritors of a deep Hellenistic tradition, fluent in both Greek and their own Aramaic dialect, Syriac. Long before the rise of Baghdad, within the quiet walls of monasteries like Erasure on the Euphrates, these scholars were already translating Greek philosophy, medicine, and science into Syriac. They did this to serve their own educational and theological needs, creating a vital reservoir of knowledge. When the Abbasid translation project began, these scholars became the indispensable linchpins. A man like Hunayn ibn Ishaq, a Nestorian Christian, was the archetype. He didn't just know Greek, he was a master of it, traveling to Byzantine lands to find the best possible manuscripts, sometimes comparing multiple copies to reconstruct a perfect original. His method was revolutionary. Earlier translations had often been painfully literal, word-for-word renderings that could obscure meaning. Hunayn insisted on translating sense for sense. He would first grasp the complete concept in Greek, then find the most precise and elegant way to express it in Syriac. Only then, often with the help of his son or other collaborators, would that refined Syriac version be translated into Arabic. This pipeline solved a fundamental problem. Direct translation from Greek to Arabic was incredibly difficult, as the two languages and their conceptual worlds were so far apart. Syriac, sharing a Semitic root with Arabic and a deep history with Greek, acted as the perfect cultural and linguistic bridge, but the challenges went far beyond words. How do you translate a geometric diagram? A translator couldn't just describe it, they had to redraw it with meticulous accuracy, ensuring every angle and proportion was preserved because the proof was in the visual logic. How do you find an Arabic term for a Greek philosophical concept that had no equivalent in the desert poetry of the pre-Islamic era? Scholars invented new terms, crafting a precise technical vocabulary that would empower Arabic as a language of science for centuries to come. This was never a story of one brilliant mind working alone. It was a sprawling, collaborative network. A Greek manuscript might be found by a merchant, purchased by a caliph's agent, delivered to the House of Wisdom, examined by a Syriac Christian for authenticity, translated by a team under Hunayn's supervision, and then checked for mathematical consistency by a Persian astronomer. The salvation of Euclid's geometry was therefore a profoundly intercultural achievement. It required the shared conviction across religious lines that this knowledge was too valuable to lose, and the humble, painstaking work of passing it, hand to careful hand, from one world into the next. While Baghdad scholars debated under the golden domes of the House of Wisdom, a different kind of preservation was underway far to the west, in the cold stone halls of European monasteries. Here there was no state salary paid in gold, no teams of specialists debating the fine points of Ptolemy's astronomy. There was only silence broken by the slow scratch of a quill and the soft turn of a parchment page. The scriptorium was not a center of innovation, but a fortress of memory. In places like Monte Cassino in Italy or St. Gall in the Alps, the work was solitary, repetitive, and driven by a sense of sacred duty rather than intellectual curiosity. A monk would spend his entire day at a wooden desk, carefully copying text by the light of a narrow window. His tools were simple but durable: a quill cut from a goose feather, ink made from oak gall and iron salts, and parchment, a far more resilient material than papyrus, crafted from the stretched and scraped skin of a calf or sheep. This was an act of devotion. Each letter formed was a form of prayer, a physical offering of labor to God. The monk might be copying a psalter, a volume of church history, or a rare classical text that had survived the long journey north. The crucial point is that he often did not need to understand the content to feel its value. His task was fidelity, not interpretation. To copy a mathematical diagram from a Greek manuscript was to preserve a sacred artifact, a vessel of ancient wisdom whose full meaning might only be unlocked by future generations. This mindset was institutionalized by rules like the Benedictine order's emphasis on ora et labora, prayer and work. Manual labor, which included the painstaking craft of copying, was seen as spiritually equal to liturgical prayer. Monasteries thus became the only stable, long-term institutions in a fractured Europe with the resources, discipline, and motivation to maintain libraries. Yet this very strength created a profound bottleneck. Monastic education focused on the quadrivium: arithmetic, geometry, astronomy, and music, but primarily for practical, liturgical purposes. Arithmetic was needed to calculate the movable date of Easter. Basic geometry and astronomy helped track the hours for prayer and the seasons of the liturgical year. This meant the manuscripts most likely to be copied and recopied were those with immediate religious utility. The profound theoretical works of Archimedes or the complex algebraic problems of Diophantus held no obvious purpose for setting the monastic schedule. They were exotic, difficult, and often written in a Greek script few could even read. So while the monks saved the physical medium, the parchment books, they often lacked the key, the language, and the advanced conceptual framework to unlock the deepest treasures inside. A brilliant Greek mathematical text could sit on a shelf in a monastic library for centuries, safe from decay but effectively invisible, waiting for a mind that could once again comprehend its language and its logic. The knowledge was physically preserved, but it remained in a deep, silent hibernation. The parchment may have survived, but its message could still be lost forever. This was the great filter of history, a silent, merciless process that decided which ideas would shape the future and which would vanish into the void. It wasn't a matter of quality, but of a brutal, pragmatic selection bias. Why do we have 13 books of Euclid's Elements on geometry, but only 6 of the original 13 from Diophantus's Arithmetica, a cornerstone of algebra? The answer lies in what medieval scribes and scholars found immediately useful. Geometry had undeniable earthly utility. It was the science of measurement, essential for architecture, for surveying land after the annual floods of the Nile, and for the precise construction of cathedrals. A monk or a craftsman could see its purpose. The abstract number puzzles of Diophantus, brilliant as they were, seemed like intellectual games with no clear application to building or prayer. Practicality was the first and most powerful criterion for survival. Alignment with prevailing worldviews was equally decisive. A text like Plato's Timaeus, which presented a geometric vision of a divinely ordered cosmos, resonated deeply with Christian and Islamic scholars seeking to understand creation through reason. It was copied endlessly. In contrast, the purely mechanical, almost playful works of Archimedes on levers and pulleys were less universally appealing, and many were nearly lost, surviving only in a handful of precious copies. Then there was the sheer, random cruelty of physical luck. The great library of Alexandria suffered multiple devastating fires. The House of Wisdom in Baghdad was utterly destroyed during the Mongol siege in the 13th century. Countless unique manuscripts, the only copies of their kind, turned to ash or were scattered to the winds in these single, catastrophic events. The brilliant 8-book treatise on conic sections by Apollonius of Perga, a work that would later become fundamental to astronomy and physics, was almost entirely erased. We know of its existence and staggering sophistication only because other authors mentioned it with awe. Only 4 of its 8 books survived the filter. The filter's effect becomes starkly clear when we look at what actually remained on European monastery shelves. For centuries, the standard mathematical textbook was not Euclid in Greek, but De Institutione Arithmetica by Anicius Boethius. This was a simplified, watered-down Latin adaptation of earlier Greek number theory. It was not a frontier of discovery, but a basic primer. Yet because Boethius was a respected Christian philosopher, and because his text was accessible, it was copied and recopied until it became the default. For 500 years, this was the mathematical diet of the European educated class, a simplified echo of a much richer tradition they didn't even know existed. The filter didn't just preserve some texts and lose others. It actively shaped an entire civilization's understanding of what mathematics even was, creating a narrowed intellectual pathway that future thinkers would have to laboriously widen again. The legacy that reached the later Middle Ages was therefore a deeply incomplete one, a puzzle with most of its pieces still missing. The thrilling question is, how would those lost pieces ever be found? The salvation of knowledge was never the work of an institution, but of individuals driven by a singular obsession. These were the bridge builders, men who spent their lives spanning the chasms between languages and cultures, one painstaking word at a time. At the forefront stood Hunayn ibn Ishaq. As a Nestorian Christian in 9th century Baghdad, his identity placed him perfectly at the crossroads of empires. He wasn't just a translator, he was a master philologist and physician who traveled into Byzantine territory, seeking out the oldest, most accurate Greek manuscripts he could find, often paying for them with his own funds. His genius lay in his method. Earlier attempts at translation were clunky, word-for-word affairs that could render a beautiful geometric proof into incomprehensible gibberish. Hunayn insisted on sense-for-sense translation. He would gather a team, his son, his nephew, other scholars, and they would first work to fully understand the concept in Greek. Then they would debate the clearest way to express it in Syriac, their shared scholarly tongue. Only after perfecting the Syriac version would they collaboratively craft the final Arabic text. This process treated knowledge as a living idea to be carefully rehomed, not a dead artifact to be stuffed and mounted. His personal motivation was a scholar's pure thirst, but it was enabled by the patronage of the caliph, who valued the work enough to reward Hunayn with a legendary payment, a sack of gold equal to the weight of the books he translated. This collaboration between individual passion and state support created an unstoppable engine for preservation. Centuries later and thousands of miles to the west, a different kind of seeker embarked on a similar quest. His name was Gerard of Cremona. In the 12th century, the intellectual landscape of Europe was beginning to stir, and rumors had reached Italy of a treasure trove of ancient wisdom, but it was all written in Arabic. The texts of Aristotle, Ptolemy, and al-Khwarizmi were said to exist in the libraries of Toledo, Spain, a city recently reconquered from Muslim rule and now a vibrant, multilingual frontier. Gerard traveled there not for conquest, but for conquest of a different kind. He learned Arabic not through formal schooling, but likely through immersion, working alongside local Jewish and Mozarabic Christian scholars who were already fluent. What he discovered in Toledo overwhelmed him. Here were entire libraries filled with the advanced works that Europe had lost centuries before. Gerard dedicated the remainder of his life to a single, monumental task, moving that library, book by book, into Latin. He translated over 80 works himself, a staggering output that included Ptolemy's masterpiece of astronomy, the Almagest, and al-Khwarizmi's groundbreaking algebra. The effort was Herculean. He wasn't just copying words, he was building an entire technical vocabulary from scratch, forging Latin terms for concepts that had been forgotten in the West. He worked until his death, and his students famously wrote that he was driven by a love of learning so profound that he abandoned his homeland for the sake of knowledge. The legacy of these bridge builders is measured in the weight of the books they left behind. Hunayn's refined Arabic versions became the standard texts for the Islamic world, fueling centuries of scientific advancement. Gerard's Latin translations became the essential textbooks of the European medieval universities. When a young scholar in Paris or Bologna opened a volume of the Almagest, they were holding the direct result of Gerard's lonely labor in Toledo, which itself was a translation of a text preserved and refined by Hunayn's team in Baghdad, which traced its lineage back to a Greek original copied by some anonymous scribe in Alexandria. This chain, forged by personal curiosity and perseverance across faiths, had successfully passed the torch through 1,000 years of darkness. The ideas were now physically present in the heart of Europe, but a final, crucial step remained. How would a society that had learned its mathematics from simplified primers react when suddenly confronted with the full, staggering depth of the ancient world's genius? The torch of learning, carried so carefully from Greek to Syriac to Arabic, now faced its final, decisive crossing. Toledo, a city of worn stone and winding streets perched on a high plateau in the heart of Spain, became the gateway. When Christian forces took the city in 1085, they conquered not just territory, but one of the greatest libraries in the known world. This was not a story of destruction, however, but of discovery. The new rulers, led by the learned Archbishop Raymond, looked upon the city's vast collections of Arabic manuscripts not as something to burn, but as something to unlock. Toledo transformed almost overnight from a Muslim capital into a unique multicultural workshop, a buzzing intellectual marketplace where the preserved knowledge of the East was systematically soldered back onto the West. Here, Muslim scholars who chose to stay, Arabic-speaking Christians known as Mozarabs, and Jewish thinkers fluent in multiple languages worked alongside Latin clerics from France, Italy, and England. The atmosphere was one of pragmatic collaboration. A bishop needed texts to strengthen the church's intellectual foundations. A king desired the practical astronomy for navigation and timekeeping, and the scholars themselves were driven by a pure, insatiable curiosity. This convergence gave birth to what historians call the Toledo School of Translators. Their method was a masterpiece of practical teamwork. Imagine a small, sunlit room. A Mozarab scholar holding an Arabic copy of al-Khwarizmi's algebra would read the text aloud, translating it on the fly into the local Romance vernacular, the everyday spoken language. Seated beside him, a Latin scholar like the indefatigable Gerard of Cremona would listen intently and then craft those spoken ideas into formal, written Latin, the academic language of all Europe. This oral, collaborative process was a democratizing force. It meant that the translator did not need to be a solitary genius fluent in both source and target languages. Instead, it leveraged the combined skills of a community, turning translation into a conversational, almost living act of interpretation. The result was a flood of texts that had been lost to Europe for half a millennium. Ptolemy's star charts, Euclid's geometry, and the revolutionary algebraic methods of the East began pouring into Latin. This was not a simple return of Greek knowledge, however. What reached the scribes in Paris and the masters in Oxford was an enriched hybrid tradition. It was Greek geometry filtered through Persian commentary, explained with Indian numerals, and refined by centuries of Islamic scholarship. This material provided the essential fuel for a new institution just then taking shape, the university. For the first time in centuries, European scholars had access to a body of knowledge that was not just practical, but profoundly theoretical and complete. The quiet, collaborative work in Toledo's scriptoriums had rebuilt the intellectual bridge, and now a continent was ready to cross it. A dusty manuscript in a Toledo library was a silent artifact. For its knowledge to truly live again, it needed to find its way into a student's hand and a teacher's lecture. This final leap from preservation to propagation happened because of a revolution in learning itself, the birth of the university. In cities like Bologna, Paris, and Oxford, a new kind of community formed, not of monks seeking spiritual perfection, but of masters and students hungry for structured, secular knowledge. These were bustling, noisy, urban institutions, and they created an insatiable demand for textbooks. Suddenly, there was a market for the very texts Gerard of Cremona and others had labored to translate. To feed this market, a new professional class emerged, the university stationers. These were not monks working in solitude, but entrepreneurs operating under strict university licenses. They maintained official copies called exemplaria of approved texts from which teams of freelance copyists could rent sections to duplicate. This system standardized the curriculum and, crucially, made books more accessible. The technology that made this possible was paper, another gift from the Islamic world that arrived in Europe via Spain and Italy. Far cheaper and faster to produce than parchment, paper allowed for more copies at a fraction of the cost. A student could now own, or at least rent, a personal copy of key texts, marking them up, arguing with them in the margins, and carrying them from lecture to lecture. This physical democratization of the page was as important as the translation itself. Yet the universities needed more than just the texts. They needed a method to think with them. This arrived in the form of Aristotle's recovered works on logic, physics, and metaphysics, which provided a powerful, systematic framework for rational inquiry. The scholastic method, with its rigorous practice of posing questions, citing authorities, and debating opposing viewpoints, trained minds to engage with complex, abstract argument. It created the perfect intellectual soil for mathematics to take root. Within this new environment, Euclid's Elements was no longer an obscure relic. It was the ultimate training manual in logical deduction, a sequence of propositions where each step followed inexorably from the last. Masters began to teach it not just for its practical geometry, but for its mental discipline. For the first time in over 700 years, Euclid's proofs became a standard part of a European scholar's education. The journey was complete. A chain of transmission that began with a Syriac monk copying Greek on parchment, passed through the collaborative workshops of Baghdad and Toledo, was now culminating in a lecture hall in Paris, where a master pointed to a geometric figure on a wax tablet, explaining a proof to students who would one day build cathedrals, chart oceans, and lay the groundwork for a scientific revolution. The idea, against all odds, was not just saved, it was back at work. The quiet work of translation was far more than a simple substitution of words. It was an act of intellectual alchemy, a high-stakes puzzle where the precise meaning of a civilization's genius had to be perfectly recast into the mold of another language. Translating poetry is an art of capturing feeling and rhythm, but translating mathematics is a science of absolute precision, where a single misplaced term can unravel an entire logical proof. The scholars in Baghdad and Toledo faced a daunting void. How do you express a Greek geometric concept that simply does not exist in the vocabulary of 7th century Arabic, a language rich in poetry and law but not yet in technical science? Their solutions were nothing short of creative genius. Sometimes they borrowed. The Persian scholar Muhammad ibn Musa al-Khwarizmi wrote a foundational text called Al-Kitab al-Mukhtasar fi Hisab al-Jabr wal-Muqabala, which means the compendious book on calculation by completion and balancing. When his work was translated into Latin centuries later, translators latched onto that key word, al-Jabr, meaning restoration or completion. They Latinized it directly into algebra, giving a name to an entire branch of mathematics. Similarly, al-Khwarizmi's own name, rendered in Latin as algorithmus, came to mean any systematic method of calculation, eventually becoming our word algorithm. This was a direct import, a new word for a new idea. Other times they invented. The Greek term for the side of a right triangle opposite the right angle was a cumbersome phrase. Arabic scholars, through their study and translation, refined the concept, and their term for it was later adopted into Latin as hypotenusa. This was not a direct translation, but a new technical term born from the process of cross-cultural explanation. The process was fraught with peril, and errors could cement themselves for centuries. A famous example involves the Greek astronomer Ptolemy's great work, the Mathematique Syntaxis. Arabic translators, in awe of its scope, referred to it as al-Magisti, meaning the greatest. When Gerard of Cremona translated it from Arabic into Latin, he transliterated this title as Almagist. The original Greek name was almost forgotten, but Ptolemy's work survived under its Arabic-born nickname. These choices were not neutral. They permanently shaped how future generations would conceptualize these ideas. The Arabic al-Jabr carried a sense of restoring a broken bone or completing an equation, a visceral metaphor that the cold Latin algebra loses. Every time a modern student writes out an algebraic equation, they are using a term forged in a 9th century Baghdad workshop, a linguistic fossil of that great transfer. This linguistic alchemy defined the very toolkit of modern science. It was a testament to the translators' deep understanding that they could build these bridges, not just between languages, but between entire worlds of thought, ensuring that the logic itself arrived intact, ready to ignite minds in a new age. But of all the texts that made the journey, one stands apart as a true intellectual catalyst. Euclid's Elements was not merely a book of geometry, it was a blueprint for the very architecture of thought. Composed in Greek around 300 years before the Common Era, it survived the long silence, was translated into Arabic in the 9th century by scholars like al-Hajjaj ibn Yusuf, and finally rendered into Latin from that Arabic version in the 12th century by Gerard of Bath. Its arrival in the medieval university was nothing short of revolutionary. For the first time in centuries, scholars held a complete, self-contained system of knowledge that moved with absolute, irresistible logic. It began with a handful of simple, undeniable statements, A point is that which has no part, a line is breadthless length. From these humble axioms, Euclid built an entire universe of truth, proposition by rigorous proposition, each new statement proven by what had come before. This method of deductive reasoning, moving from the general to the specific with ironclad certainty, was a revelation to a world steeped in faith and authority. Here was a different kind of authority, one based not on tradition or revelation, but on pure, transparent logic that any rational mind could follow and verify for itself. Theologians like Thomas Aquinas saw in this structure a powerful parallel for understanding divine truth. If one could build an entire edifice of geometry from a few self-evident principles, could one not also build a rational understanding of God's creation? Aquinas famously employed a similar logical method in his Summa Theologica, using structured arguments and objections to construct a systematic theology. The influence rippled far beyond the church. The very idea of constructing a legal argument, of building a case from foundational principles toward an inescapable conclusion, was shaped by this model of axiomatic proof. To master the elements became the supreme intellectual rite of passage. A scholar was not considered truly educated until they had worked through its 13 books, internalizing its relentless logic. This did more than teach geometry. It trained generations of minds to think in terms of proof, evidence, and logical consequence. The Greek ideal of mathematics as a pursuit of eternal, demonstrable truth was now permanently embedded into the Western intellectual DNA. The quiet act of copying and translating this single text had not just saved a set of theorems about triangles and circles, it had reintroduced an entire civilization to the power of reason itself. The preserved knowledge of the ancients was not a dead weight to be carried, but a living seed to be planted. Within the vibrant intellectual climate of the Islamic Golden Age, the classical texts were not simply memorized, they were actively questioned, corrected, and built upon. This was not an age of preservation for its own sake, but of profound and original innovation. The translation centers served as dynamic incubators, where Greek logic, Indian calculation, and Persian astronomy cross-pollinated to create entirely new branches of mathematics. Take the Persian poet and mathematician Omar Khayyam. Confronted with cubic equations, problems that had stumped the Greeks, he did not give up. Instead, he made a brilliant conceptual leap. Since algebraic methods of the time fell short, Khayyam turned to geometry. He showed how the solution to a cubic equation could be found precisely where a carefully constructed parabola intersected a circle. This was a breathtaking synthesis, using the geometric tools of the Greeks to solve algebraic problems they themselves could not crack. It was a completely new way of thinking about the relationship between shape and number. Meanwhile, driven by the needs of astronomy and timekeeping for prayer, trigonometry evolved from a scattered set of tools into a full-fledged systematic science. Scholars like al-Battani compiled incredibly accurate astronomical tables and clearly defined the trigonometric functions we use today, like the sine and cosine, establishing the relationships between the sides and angles of a triangle as a distinct field of study. Perhaps the most transformative adoption was the decimal positional number system from India. Islamic mathematicians fully embraced this system, including the revolutionary concept of zero as both a placeholder and a number in its own right. They perfected its use in calculation, replacing cumbersome methods that relied on counting boards or abacuses. This was a shift so fundamental it is hard to overstate. Contrast this with the state of mathematics in Europe at the very same time. While scholars in Baghdad and Cairo were manipulating equations and calculating signs, most European merchants, scholars, and even kings were still struggling with Roman numerals. Try multiplying mmxliv by CLII using only pen and paper. It was a slow, tortuous process ill-suited for complex calculation or advanced theory. European mathematics remained largely practical, focused on the arithmetic needed for trade, land measurement, and the liturgical calendar. The gulf between these two mathematical worlds could not have been wider. One was dynamic, theoretical, and equipped with a powerful notation, while the other was static, practical, and held back by a clumsy numerical language. This stark difference highlights the true legacy of the translation centers. They were not time capsules locking knowledge away, but active laboratories. By gathering the best ideas of the known world into a common language, they created the conditions for a great leap forward, forging the sophisticated mathematical tools that would eventually empower the entire world. The great libraries were monuments of collective memory, but the survival of a single manuscript often hinged on the passion of one person. Beyond the walls of state-funded academies and monastic scriptoria, a parallel, shadow network of knowledge thrived in the private collections of wealthy patrons and obsessive scholars. These personal libraries were not bound by institutional rules or religious orthodoxy. They were reflections of individual curiosity, assembled through a mix of diplomacy, scholarly exchange, and sometimes conquest, and they acted as a vital, decentralized safety net for the fragile written word. In the waning years of the Byzantine Empire, the scholar Michael Psellos served as a high official and teacher in Constantinople. His true passion, however, was for the ancient Greek philosophical and scientific texts that were becoming rare even in their homeland. He actively sought them out, studied them deeply, and wove their ideas into his own writings, ensuring that the logical methods of thinkers like Aristotle and the mathematical concepts of Archimedes remained part of a living conversation in the East, even as Western Europe had forgotten them. His private collection was a personal fortress for ideas under siege. Far to the west, another kind of patron was at work. Frederick II, the Holy Roman Emperor, ruled a cosmopolitan court in Sicily, a crossroads of Latin, Greek, and Arabic culture. He was fascinated by the natural world and by the mechanics of power, and he saw knowledge as a tool for both. He actively invited Jewish, Muslim, and Christian scholars to his court, commissioning translations and encouraging debates on mathematics, optics, and falconry. His personal interest turned his court into a magnet for texts and the minds that could understand them. These private collections possessed a unique mobility and flexibility that large institutions lacked. A monastic library was anchored to a specific place, vulnerable to local conflict or disaster. A private library, however, could travel with its owner or be dispersed through inheritance or sale. When a scholar passed, their books might be sold to pay debts or bequeathed to a favorite student, sending ripples of knowledge out into new circles. A single precious codex, once owned by a Byzantine official, could find its way via Venetian traders to the desk of a humanist scholar in Florence. This organic, almost random movement of texts created unexpected pathways for survival. A work deemed too specialized or unconventional for a monastic copying list might find a perfect home in the private collection of a wealthy merchant fascinated by astronomy or a nobleman intrigued by engineering. These shadow libraries were the ultimate hedge against total loss. While the great center in Baghdad was tragically destroyed, countless individual manuscripts from its collections had already circulated into private hands across the Islamic world, saved from the flames by their very dispersion. The story of preservation, therefore, is not just one of mighty institutions, but of countless individual acts of acquisition and care, a silent, scattered conspiracy of curiosity that kept the embers of knowledge alive in 1,000 different rooms, waiting for the moment when a brighter fire could be lit. A brilliant idea is powerless without a page to carry it. The survival of classical mathematics hinged not just on the minds of translators, but on the very physics of the materials they wrote upon. Two different substances became the guardians of this legacy, each with its own strengths and vulnerabilities, shaping the flow of knowledge across continents. In the damp, cool monasteries of Europe, the chosen medium was parchment. This was not paper, but the meticulously prepared skin of a calf, sheep, or goat. The process was arduous, involving soaking, stretching, scraping, and drying the hide to create a smooth, durable writing surface. The result was remarkably tough. Parchment could survive centuries of handling. It resisted tearing, and if you made a mistake, you could carefully scrape the ink off and write again. This resilience made it ideal for preserving a sacred text or a legal charter meant to last for generations. But that durability came at a staggering cost. Producing a single Bible might require the skins of 200 animals, an enormous investment of livestock and labor. This meant every page was precious, and the decision to copy a text was a serious economic commitment. A monastery might choose to recopy a psalter or a volume of saints' lives long before it would commit resources to a complex, puzzling Greek mathematical manuscript. Parchment ensured longevity, but its expense acted as a fierce filter on what was deemed worthy of that longevity. Meanwhile, across the Islamic world and flowing into Europe via Spain, a different guardian was at work: paper. Invented in China centuries earlier, the technology was perfected in cities like Baghdad and Samarkand. Paper was made from a pulp of linen rags or plant fibers, mashed in water and pressed into sheets. It was a revolution in information economics, far cheaper and faster to produce than parchment. Paper allowed for the creation of many more copies at a fraction of the cost. This was the material that fueled the translation workshops of Toledo and the bustling university stationers' shops. It democratized access, allowing students to own personal copies of texts. Yet paper had its own Achilles heel. It was more vulnerable. Dampness could cause it to mold and disintegrate. Insects and rodents found it more palatable than treated animal skin. A paper book required careful storage in a dry place to survive the centuries, while a parchment codex could endure much harsher conditions. The choice of material, dictated by local resources and climate, created two different models of preservation. One of high-cost, high-durability archiving, and another of lower-cost, wider dissemination. Alongside this material shift came a profound change in format, the triumph of the codex over the scroll. Imagine trying to study a complex geometric proof on a long, continuous roll of papyrus or parchment. To check a reference from earlier in the text, you would have to awkwardly scroll back through feet of material. The Codex, our modern familiar book with separate pages bound at one edge, changed everything. A scholar could now flip easily between pages, comparing a diagram on one leaf with a theorem explained 50 pages earlier. This made navigating dense, argumentative texts like Euclid's Elements or al-Khwarizmi's algebra not just possible, but practical. The Codex also protected its contents better, with sturdy wooden or leather covers shielding the pages. This seemingly simple innovation, the bound book, was as crucial as the translation itself. It turned a static repository into an interactive tool, enabling the kind of cross-referencing and deep study that advanced mathematics demands. So the legacy that reached us was shaped by a silent partnership, the rugged, costly endurance of parchment in European monasteries that saved unique copies from total decay, and the prolific, accessible spread made possible by paper in the Islamic and later European worlds, which allowed ideas to multiply and reach critical mass. The thoughts of Euclid survived because they were literally embedded in the skin of a goat and later woven into the cloth of a discarded linen shirt, two humble substances that gave abstract genius a physical form tough enough to outlast empires. The fragility of this entire chain, however, is perhaps best understood through a single, miraculous book. In a quiet library in Constantinople around the year 1229, a pious scribe faced a common dilemma. Parchment was expensive, and he needed to create a new prayer book. His solution was to take an older manuscript, one he likely saw as obsolete, and carefully scraped the ink from its pages. He then washed the skin, turned it sideways, and wrote his liturgical text over the faint, ghostly traces of the old. This recycled book, called a palimpsest, was a practical act of medieval recycling. But what the scribe had unknowingly erased was the only surviving copy of a work by Archimedes of Syracuse, the ancient world's greatest mathematical mind. The text was his method of mechanical theorems, a revolutionary work where he explained how he used mechanical concepts, like balancing shapes on a theoretical lever, to discover new geometric truths. For centuries, this treasure lay invisible beneath the prayers, passing through collections unseen. It was briefly noted by a scholar in 1906, who glimpsed faint Greek lines beneath the script, but the technology to read it did not exist. The book then disappeared again into private hands for most of the 20th century, its secret intact. Its dramatic modern recovery began when it resurfaced at an auction in 1998. Scientists then used a technique called multispectral imaging, bathing the pages in different wavelengths of light. The prayer book ink, made from medieval oak gall, would recede under certain lights, while the original Archimedes ink, composed of an older carbon-based formula, would glow faintly from beneath. Slowly, line by line, the erased text of Archimedes was pulled back from oblivion. The recovered work showed that his thinking was even more profound than previously known, using ideas that foreshadowed calculus by nearly 2,000 years. This was not a story of careful institutional preservation, but of breathtakingly good luck, a single copy surviving against all odds because its material value as a blank parchment outweighed its intellectual value to a medieval scribe. A similar, quieter rediscovery changed the course of mathematics centuries earlier. In the 15th century, a German scholar named Regiomontanus traveled to Italy, scouring libraries for ancient texts. In the Vatican archives, he found a more complete manuscript of Diophantus's Arithmetica than any known in Western Europe. This was the same text that had been filtered down to just 6 books, but this version contained deeper, more challenging problems. Regiomontanus recognized its worth and planned to publish it, though he died before he could. The manuscript continued to circulate, and a century later, a copy reached the French magistrate and amateur mathematician Pierre de Fermat. As he read Diophantus's problems in the margin of his own copy, Fermat was inspired to jot down a note of his own, stating he had a marvelous proof for a certain equation that the margin was too small to contain. This casual note became the legendary Fermat's last theorem, a puzzle that would tantalize and defeat mathematicians for over 350 years. The entire saga, one of the most famous in mathematical history, began with the chance rediscovery of a single, more complete manuscript in a forgotten archive. These stories of near-total loss and last-minute recovery force a humbling realization. Our entire understanding of intellectual history is built on a shockingly thin foundation, a scattered collection of pages that survived war, reuse, neglect, and pure accident. Each major work we have represents countless others that vanished without a trace. The narrative of preservation is not a smooth, inevitable river, but a flickering torch passed through a labyrinth, its flame guarded as much by random chance as by deliberate design. Behind every saved manuscript was a person who chose to look past the boundaries of their own world. For scholars like Gerard of Aurillac, the quest for knowledge was a perilous pilgrimage. He would later become Pope Sylvester II, but in his youth, he was a monk driven by an insatiable curiosity that led him from the relative safety of France to the frontier monasteries of Catalonia in Spain. There, he encountered the advanced mathematics and astronomy preserved in Arabic texts, a world of learning utterly alien to the Europe of his birth. He mastered the use of the abacus and the astrolabe, tools of calculation and observation that seemed almost magical to his contemporaries. When he returned home and began to teach these concepts, he did not receive universal praise. Instead, he faced deep suspicion and whispers of heresy. In an age where intellectual authority was tightly bound to religious orthodoxy, introducing knowledge from non-Christian sources was dangerously transgressive. His brilliance earned him the sinister nickname, the Magician Pope, a label that clung to his legacy for centuries, reducing his scholarly passion to a rumor of demonic pact. The danger was not merely social but profoundly physical. To seek knowledge meant to travel, and medieval travel was a harrowing gamble. A scholar like Gerard of Bath, who journeyed from England to Sicily and Antioch, faced bandits on lonely roads, shipwreck in treacherous seas, and the constant threat of illness in unfamiliar lands. There were no safe passages, only calculated risks. Political instability could erase a lifetime's work in a single night. A scholar might spend decades building a personal library, only to see it scattered or burned in a local conflict or a shift in royal favor. The very centers of learning were fragile. The great library of the Fatimid Caliphate in Cairo, the House of Wisdom in Baghdad, these monuments to collective intellect could be reduced to rubble by invasion or civil war, their keepers scattered or gone. Yet the most demanding sacrifice was often the quietest, the sheer, monumental dedication of a lifetime. To become a bridge between worlds required mastering languages not through modern courses, but through immersion, painstaking comparison, and often without a single reliable dictionary. It meant copying thousands of pages by hand, checking each line for error, knowing that a single mistranslated term could corrupt an idea for generations. These individuals were not pursuing tenure or fame. They were often working in obscurity, driven by a love of wisdom, by philosophia in its original, profound sense. Their reward was not wealth or security, but the solitary satisfaction of pulling a brilliant idea back from the edge of oblivion and ensuring it could light the way for those who came after. This human cost, the suspicion, the danger, the lifelong toil, was the hidden price paid for every theorem and diagram that eventually found its way into the modern world. Their legacy is a reminder that knowledge does not preserve itself. It requires custodians brave enough to cross borders, both on maps and in the mind. The story of mathematics was never unfolding in a vacuum. To understand its remarkable survival, we must place it beside the fates of other great streams of classical thought. Consider the vast body of medical knowledge compiled by the physician Gall. His works, like those of the geometers, were translated extensively in Baghdad by the very same scholars such as Hunayn ibn Ishaq. Gallen's theories on anatomy and treatment became the foundation of Islamic and later medieval European medicine for centuries. His path to preservation was nearly identical, moving from Greek to Syriac to Arabic and finally into Latin, saved by the same networks of translation. Philosophical works, especially the complete corpus of Aristotle, followed this route with world-altering consequences. His texts on logic, physics, and metaphysics, recovered through the Arabic translations, would fundamentally reshape European theology and science, providing the logical framework that made advanced mathematical inquiry intellectually respectable. Yet when we turn to literature, the picture grows starkly different. Of the hundreds of plays written by the great Greek tragedians like Sophocles and Aeschylus, only a tiny fraction survive. Their works, deeply tied to the specific religious festivals and civic life of ancient Athens, held less obvious utility for a medieval monk in Burgundy or a scholar in Baghdad. A play was a cultural artifact, its value more contingent, while a geometric proof claimed a universal, impersonal truth. This comparison reveals a crucial filter. Knowledge with clear, enduring utility or a logical structure that transcended culture had a far greater chance of making the perilous journey. Mathematics possessed both. Its truths were not about the whims of gods or the politics of city-states. They were about the immutable relationships between numbers and shapes, truths that remained identical in Greek, Arabic, and Latin. Furthermore, its utility was a powerful engine for preservation. Astronomy needed trigonometry to chart the stars and calculate calendars. Optics relied on geometry to understand the behavior of light. Even architecture demanded precise calculation. This practical anchor gave mathematics a compelling reason to be continuously copied and studied, where a volume of lyric poetry might simply gather dust. Seeing this broader landscape allows us to recognize the translation movement for what it truly was: not a miraculous accident that saved one discipline, but a conscious, sprawling project of cultural synthesis. Medieval scholars across the Mediterranean world were actively gathering the intellectual inheritance of antiquity, assessing it, translating it, and weaving it into the fabric of their own civilizations. They were building a new library of humankind, and mathematics earned its central place on those shelves not by chance, but by the undeniable power and utility of its logic. This wider view makes the achievement more profound, showing a coordinated effort to salvage the very tools of reason itself from the tide of time. The silent work of preservation required a specific kind of sanctuary. The architecture of these early centers of learning was not an afterthought, but a deliberate, functional blueprint for protecting fragile knowledge. In a European monastery, the heart of this effort was the scriptorium. This was a room engineered for a single, painstaking task. Large, north-facing windows were carefully positioned to flood the space with steady, cool light, minimizing harsh shadows and the damaging heat of direct sun that could warp parchment or fade ink. Within this hall of light, each scribe worked at an individual carrel, a small wooden desk with partitions on 3 sides. This simple design created a cell of concentration, shielding the monk from the movements and whispers of his brothers, allowing him to descend into the silent world of the text before him. His tools were arranged with ritual care: the inkhorn, the quills, the pumice stone for smoothing the parchment, and the ruler for scoring straight, guiding lines. The manuscripts themselves, once copied, were stored in heavy wooden chests called armaria, often locked to protect these precious, labor-intensive assets. The entire environment was a climate-controlled vault long before the concept existed. Thick stone walls insulated against damp and sudden temperature shifts, while the routine of monastic life avoided the soot and smoke of open fires in this sacred space. Every architectural choice, from window placement to desk design, served to remove distraction and physical hazard, making the scriptorium a machine for copying with flawless accuracy. Across the Mediterranean, the Islamic madrasa developed a different architectural answer to the same fundamental need. These schools were often built around a central courtyard, a tranquil, shaded oasis with a fountain or pool at its center. The sound of water provided a gentle, calming backdrop, masking street noise and cooling the air. Student rooms, small and Spartan, lined the upper floors, while the ground level housed larger halls for teaching and, crucially, the library. Here, books were not locked in chests but stored in wall niches or on shelves, often chained to reading desks to allow access while preventing theft. The design promoted a rhythm of life that blended community and solitary study. Students could gather in the courtyard for discussion under the open sky, then retreat to their rooms or the library for private contemplation and copying. The courtyard itself acted as a natural climate regulator, its open space promoting air circulation to keep the precious paper manuscripts dry in humid conditions. Whether in the silent, focused carrel of a monastery or the communal yet ordered courtyard of a madrasa, the architecture itself was a silent partner in the work. These spaces were technologies of the mind, physical instruments crafted to sustain the fragile, human act of passing an idea, unchanged from one generation to the next. The survival of a theorem began with the angle of the light falling on a page. Yet the struggle against entropy never truly ends, it simply changes its form. We live in an era of unprecedented information creation, where more data is produced in a single day than was written in all of medieval Europe. But this digital deluge comes with its own profound vulnerability. Our modern scrolls are hard drives, our codices are complex software files, and our great libraries exist as server farms humming in climate-controlled buildings. The threat of a digital dark age is not science fiction, but a quiet concern among archivists and historians. It is the fear that our own civilization's records, its art, its science, its everyday communications, could become as unreadable to future generations as a Syriac palimpsest was to a 19th-century scholar without multispectral imaging. This new struggle for preservation creates a startling, direct parallel with the monastic scribes and translators of 1,000 years ago. Our modern translation centers are organizations like the Internet Archive and Project Gutenberg. Their mission is not to move knowledge from Greek to Arabic, but from obsolete file formats to readable ones, from decaying magnetic tape to stable cloud storage. They are fighting their own version of bit rot, the slow, silent corruption of digital data, which mirrors the physical decay of papyrus in a damp cellar. The medieval scribe who meticulously copied a manuscript onto fresh parchment to save it from crumbling is performing the same essential act as the software engineer who writes a program to migrate data from a floppy disk to a solid-state drive. Both are translators moving precious information from a dying medium to a living one. The challenge of accessibility is identical in spirit, only the tools have changed. A 12th century scholar needed to learn Arabic to access al-Khwarizmi's algebra. A researcher today might need to find a working machine that can read a 5 1/4-inch floppy disk, or locate software that can decode a proprietary word processor file from the 1980s. Format migration is our era's language translation, and just as the medieval effort relied on the patronage of caliphs and bishops, digital preservation hinges on the modern equivalent's institutional funding, grants, and often the sheer volunteer passion of individuals who believe, like Gerard of Cremona, that this knowledge is too valuable to lose. This comparison reframes those quiet monks in their carols as the original information scientists. They were developing protocols for data integrity, creating standardized copy editing practices, and building distributed backup systems by sending duplicate manuscripts to different monasteries. Their work gives us a crucial historical perspective. It tells us that the urge to preserve is a constant of civilization, and that the technical challenges, while daunting, are solvable with patience and ingenuity. More importantly, it makes their ancient mission feel urgently relevant. We are not so different from them. We are simply the latest generation of scribes standing at our own technological frontier, making choices right now about what deserves to be saved, what format will last, and how we will ensure that the brilliant ideas of our time, and all the times before ours, remain a living light, not a forgotten code in an unreadable file. Their success feels inevitable only because we live in its aftermath. To measure the true scale of their achievement, we must briefly step into the darkness they held at bay. Imagine a world where the fragile chain of transmission finally snapped. In this alternate history, the quiet scriptoriums fall silent one by one, their scribes never copying the last surviving Greek mathematical texts. The translation workshops in Baghdad and Toledo never form, or are destroyed before their work is done. The consequence is not merely the loss of a few old books, but the severing of an entire lineage of thought. In this world, the works of Euclid, Archimedes, and Ptolemy vanish completely from the West, their names fading into the vague legends of a lost golden age. The sophisticated astronomy of the Islamic world, built upon that Greek foundation, remains confined to its own regions, never crossing the Pyrenees into Europe. The decimal system and the concept of zero, those revolutionary tools of calculation, never replace the cumbersome Roman numerals, What would such a world look like? Without the rigorous logic of Greek geometry, the very language of precise engineering is muted. The great Gothic cathedrals, whose soaring vaults are exercises in stone mathematics, might never rise or would take a cruder, more tentative form. The intricate gearwork of advanced clocks, essential for navigation, would lack the theoretical underpinnings to develop beyond simple timekeeping. Cartography would remain a matter of sketch and superstition, with no coordinate system or method to accurately project a spherical world onto a flat page, leaving ocean navigation a terrifying gamble of dead reckoning. The Renaissance, that great reflowering of art and science, was fundamentally ignited by the rediscovery of classical texts. If those texts were not merely forgotten but utterly gone, that movement either never happens or becomes something else entirely. A revival with nothing concrete to revive, a search for wisdom with no library to consult. The scientific revolution of the 16th and 17th centuries, built by figures who stood on the shoulders of these translated giants, is delayed for centuries, perhaps forever, altering the trajectory of human technology and understanding. This thought experiment is not mere speculation. It highlights a profound truth about the nature of progress. Innovation rarely springs from a vacuum. It requires a foundation, a shared toolkit of concepts and methods upon which new layers can be built. The translation centers did not just rescue relics. They preserved the foundational tools, the logic of proof, the language of calculation, the models of the cosmos, that allowed subsequent generations to ask new questions and see further. They saved the intellectual seed corn, ensuring that after the long winter, a harvest was still possible. The quiet act of copying a manuscript, then, was not an exercise in nostalgia. It was an act of faith in a future those scribes would never see, a deliberate planting of a forest whose shade they knew they would never enjoy. The true scale of this rescue mission becomes clear only when we look beyond the celebrated names. For every Hunayn ibn Ishaq or Gerard of Cremona whose work echoes through history, there were countless others whose hands and hearts made their breakthroughs possible. This was a vast human machine, and its most essential cogs were the anonymous scribes. Day after day, in the chill of a stone scriptorium or the quiet corner of a scholar's house, they bent over their desks. The work was physically grueling. A scribe's hand would cramp around the quill, his eyes strain in the dim light, his back ache from hours of perfect stillness. A single mistake, a smudged letter, a miscopied number in a geometric proof could render an entire page useless, wasting precious parchment and days of labor. Their task demanded not just literacy, but immense discipline and patience, a willingness to submerge their own identity into the flawless reproduction of another's genius. They were the unsung infrastructure of memory, and without their quiet, repetitive devotion, not a single line of Euclid would have survived, but parchment, ink, and a scribe's sustenance cost money. This is where the patrons entered the story, the often overlooked financiers of the intellectual revival. Think of the Abbasid caliphs who funded the House of Wisdom not as a charity, but as a strategic investment in cultural prestige and practical innovation. Or consider wealthy merchants and noble families who commissioned translations and built private libraries, using knowledge as a form of social capital. In Europe, bishops and monastic abbots allocated scarce community resources, the sale of wool, the yield from vineyards, to support the scriptorium. Purchasing the fine vellum for a luxury manuscript of the Almagest could represent a significant portion of a monastery's annual budget. This patronage was a vote of confidence in the future, a belief that preserving this abstract knowledge had a value that justified real, tangible cost. It turned the act of thinking into a viable profession. Then there were the organizers, the librarians and catalogers who fought the chaos of accumulation. A library of 1,000 manuscripts is a treasure trove, but without order, it is a labyrinth where any specific text can be lost forever. These individuals devised early classification systems, created inventories, and maintained the delicate environment that kept books from succumbing to damp or pests. They were the guardians of the gateway, ensuring that when a scholar like Gerard of Bath arrived seeking a specific Arabic text on astronomy, it could actually be found on a shelf, not buried under a pile of unrelated volumes in a dusty corner. Finally, we must acknowledge the traders and travelers, the circulatory system of this entire network. Knowledge moved on the same routes as silk and spices. A caravan winding along the Silk Road might carry not just bolts of cloth, but a carefully wrapped copy of an Indian mathematical treatise. A Venetian galley crossing the Mediterranean, its hold full of grain, could also be transporting a scholar like Gerard of Cremona himself, or a chest of manuscripts purchased in Alexandria bound for a bookseller in Palermo. These commercial arteries carried ideas between cultures, creating the chance encounters and long-distance exchanges that allowed a text preserved in a Syrian monastery to eventually resurface in a Spanish library. The story of preservation, therefore, is less a tale of lone genius and more a lesson in resilient systems. It required a stable flow of resources, a social consensus that learning held value, and a network of people, from the camel driver to the caliph, each performing a small, critical role in a project whose ultimate success they would never live to see. Their collective effort built a bridge across time, not with a single arch but with countless humble stones. The preserved texts did not simply gather dust on university shelves. They became a slow-burning fuse, igniting a chain reaction that would reshape the world. By the 15th century, a new breed of scholar had emerged, the humanist, driven by a desire to return to the purest sources of ancient wisdom. Figures like the German mathematician Regiomontanus typified this shift. He was no longer content with the Latin translations from Arabic that had first revived learning. He sought out the original Greek manuscripts themselves, traveling to Italy to scour monastic and private collections. His goal was to compare these originals with the medieval versions, to strip away any errors introduced through centuries of copying and translation, and to restore the pristine logic of the ancients. This critical, comparative approach was revolutionary. It combined the deep mathematical tradition kept alive through the medieval universities with a renewed reverence for the original Greek texts now being rediscovered. Regiomontanus did not just preserve, he synthesized and advanced, writing influential new works on trigonometry that cleared the path for the astronomical revolution to come. The stage was now set, but one final invention was needed to turn this scholarly revival into a continent-wide transformation. That invention was the mechanical printing press. When Johannes Gutenberg perfected movable type around the middle of the 15th century, he created a force multiplier for knowledge unlike anything since the founding of the great libraries. For the first time, a text could be reproduced not just accurately but identically in hundreds or thousands of copies. The translation centers had performed the essential, painstaking work of creating corrected, authoritative versions of Euclid, Ptolemy, and Archimedes in languages scholars could read. The printing press now placed these perfected texts onto a new, unstoppable conveyor belt. The Elements of Euclid was among the very first scientific works printed. Its flawless diagrams and logical proofs now guaranteed identical in every copy from Rome to Krakow. This created something unprecedented, a shared, stable intellectual foundation across all of Europe. A student in Paris, a painter in Florence, and a cleric in Poland could now study from the exact same page, reference the same theorem, and build upon the same unshakable base. This was the direct, material link between the quiet scriptoriums of the past and the explosive future. The printers did not need to commission new translations or hunt for manuscripts. The foundational work had already been done. They simply took the raw material provided by centuries of preservation and set it loose upon the world. With this shared toolkit now in the hands of thousands, the conditions were perfect for a cascade of insight. The stage, meticulously prepared by scribes, translators, and patrons across a millennium, was finally ready for its principal actors, minds who would use this recovered legacy to see the universe anew. But this remarkable story of rescue is not without its shadows. The great transfer of knowledge from east to west was a bridge built across a deep chasm of power, and it forces us to ask a difficult question. When the Latin West finally received the enriched legacy of Greek mathematics, did it acknowledge the hands that had kept it alive for centuries? The historical record is often uncomfortably silent. For a long time, the standard narrative in Europe spoke of a rediscovery of Greek wisdom, as if these texts had been hibernating in a cave waiting to be found. The immense creative labor of Persian, Arab, Jewish, and Syriac Christian scholars, the centuries of translation, commentary, and groundbreaking innovation, was frequently minimized or erased. The works of al-Khwarizmi or al-Batani, when they appeared in Latin, were sometimes presented without their authors' names, or those names were so Latinized they became unrecognizable. This created a distorted lineage, a history of ideas that seemed to leap miraculously from ancient Athens to Renaissance Florence, skipping over the vibrant intellectual world in between. This is where the modern concepts of cultural sharing and appropriation become painfully relevant. To call the entire medieval transfer an act of appropriation is too simplistic, as it ignores the collaborative, multi-faith nature of the translation centers themselves. It was, in its ideal form, a shared project of humanity, yet the subsequent forgetting, the failure to credit that chain of transmission in the West's own storytelling, represents a profound ethical lapse. It is the difference between a grateful guest who acknowledges the cook and one who simply takes the meal and claims to have invented the recipe. Giving full credit is not just about historical accuracy, it is about justice. It restores a more complete, more truthful story of human achievement, one that shows how our collective intellect has always been woven from many threads. This medieval dilemma echoes powerfully in modern debates. The fight for open access to scientific research asks who gets to benefit from humanity's knowledge, mirroring the ancient question of which monasteries or courts had access to precious manuscripts. Discussions about repatriating cultural artifacts ask how we rightfully steward the physical evidence of a culture's genius, much like questioning where a uniquely important translation should rightfully reside. The legacy of the translation centers offers a guiding principle, the idea of knowledge as a global commons. They succeeded not by hoarding, but by translating, not by claiming ownership, but by ensuring transmission. Their greatest lesson might be that true preservation is not just about saving a text from physical decay, but about honoring the entire, interconnected community of minds that made its survival possible. To tell the full story is to complete the work they began. The symbols on this page are the final, silent victory of a 1,000-year rescue mission. Every time you write a number, you are using the direct legacy of those translation centers. Our modern mathematical notation feels so natural we forget it is a language, one that was assembled piece by piece across continents. The most revolutionary piece was the set of digits we call Arabic numerals 0 through 9. Their story begins in India, where mathematicians developed a decimal positional system, including the profound concept of 0 as a number, not just a placeholder. When these ideas reached Baghdad, scholars like al-Khwarizmi recognized their power and championed their use. His works, traveling west to Toledo and beyond, introduced Europe to a system infinitely superior to Roman numerals. Try multiplying 67 by 143 using Roman numerals. The process is a labyrinth of clumsy addition. Now do it with the Indian system, where the position of a digit defines its value. The efficiency is staggering, transforming calculation from an arcane art into a streamlined tool for commerce, science, and navigation. This was not a simple adoption but a fusion. The forms of the digits themselves evolved as they moved, taking the shapes we recognize today in the hands of European scribes. Alongside the numbers, the very grammar of mathematics evolved from words into signs. The plus and minus symbols likely began as mercantile shorthand in German warehouses, quick marks on a ledger to indicate surplus or deficit cargo. Over time, they shed their commercial origins and entered the scholar's study, becoming universal symbols for addition and subtraction. The most poetic invention might be the equal sign, crafted by the Welsh mathematician Robert Record in 1557. Frustrated by the tedious repetition of the phrase, "is equal to," he chose two parallel lines of identical length because, as he wrote, nothing could be more equal than them. His inspiration for the concept of mathematical equality, it flowed directly from the logical structure of Greek geometry, recovered and refined through centuries of translation. This efficient symbolic language did more than speed up arithmetic. It liberated thought. Before this notation, complex problems had to be described in long, winding sentences. Algebra was literally rhetorical, a spoken art. With a compact set of symbols, relationships could be written down, seen, and manipulated visually. An equation became a snapshot of a logical relationship, allowing the mind to operate on abstractions directly. This shift made possible the abstract leaps of a Newton or a Leibniz, who could not have built calculus with words alone. The translation movement's ultimate gift, then, was not merely the content of the texts it saved, but the very medium it helped create. It gave us the silent, precise alphabet in which the laws of the universe are now written. The meticulous habits of those medieval scribes never truly vanished. They simply evolved, becoming the invisible backbone of modern scholarship. When a historian today opens a critical edition of a classical text, they are holding the direct intellectual descendant of a manuscript prepared in a 9th century Baghdad workshop. The core methods are startlingly unchanged. First, there is the practice of collation, comparing every surviving copy of a text, word by word, to identify scribal errors and reconstruct the original author's intent. This is exactly what Hunayn ibn Ishaq did when he traveled to find multiple Greek manuscripts, judging which version was most accurate. Today, this might involve digitally scanning fragments from libraries in Oxford, Cairo, and Istanbul, using software to align variations, but the goal is identical: to clear away the noise of centuries and hear the original voice. Then comes the commentary, the scholar's explanation woven around the ancient text. Medieval translators often surrounded their Arabic versions with extensive marginal notes, clarifying difficult terms or connecting ideas to contemporary knowledge. Modern scholars do the same, publishing volumes where a single line of Archimedes is followed by pages of historical context, mathematical explanation, and references to later influences. This tradition of building layers of understanding around a fragile core is a direct inheritance. Finally, there is the creation of a specialized lexicon. Just as those translators forged a new Arabic vocabulary for Greek science, modern projects create exhaustive databases of technical terms, tracking how a word like element or theorem shifted meaning across languages and centuries. These are not dusty academic exercises, they are the maintenance manuals for our intellectual heritage, ensuring that recovered knowledge remains comprehensible and alive. The most spectacular proof of this living tradition is the international effort to read the Archimedes Palimpsest. Here, a team of classicists, medieval historians, conservators, and imaging scientists worked for over a decade, their collaboration mirroring the multicultural teams of Toledo. The philologists deciphered the faint Greek letterforms, the historians placed the discoveries in context, and the physicists developed new technologies to see the ink. This was not a lone genius in a library. It was a symphony of specialized skills, united by the same driving purpose that animated Gerard of Cremona, a shared conviction that this erased text was worth any effort to restore. Their work recovered Archimedes' revolutionary method, a concept that foreshadowed calculus because a medieval scribe had valued the parchment more than the writing, and a modern team valued the writing more than the parchment. This cycle of loss and recovery continues today with digital palimpsests, as researchers use spectral imaging to read papyri carbonized by the eruption of Vesuvius, or apply artificial intelligence to reassemble fragments of the Dead Sea Scrolls. The tools have transformed from quills to quantum sensors, but the mission remains constant: to listen for the faintest whispers from the past and amplify them for the future. The legacy of the translation centers is not a closed chapter in a history book. It is an active verb, a way of working that continues to pull brilliant ideas back from the brink of silence. That legacy of quiet dedication echoes in every modern classroom and laboratory. The story of these translation centers is not merely a chapter in the history of science. It is a profound testament to human resilience and the stubborn, enduring power of an idea. Consider the chain, link by link, that connects us to antiquity. It required the silent focus of a monk in his cold carrel, copying symbols he may not have fully understood, driven by a vow of obedience. It demanded the brilliant, synthesizing mind of a scholar in Baghdad, fusing traditions under the patronage of a caliph who dreamed of Aristotle. It called for the courage of a traveler like Gerard of Cremona, abandoning his homeland to spend a lifetime unlocking a foreign library. This was not a coordinated effort by a single empire or faith. It was a sprawling, centuries-long coalition of individuals from wildly different cultures and religions who made a collective choice, again and again, to be bridges for knowledge, not its gatekeepers. They saved the logical tools of classical mathematics not for personal glory or territorial gain, but from a deeper sense of duty to truth itself, a conviction that this wisdom belonged to all of humanity and was worth any sacrifice to preserve. Their ultimate success is measured in the world we inhabit. Their legacy is the very fact that we can calculate a rocket's trajectory, engineer a pandemic-ending vaccine, or map the genome of an ancient plant, all using a shared, global language of logic and number that they painstakingly translated and transmitted. As we now navigate our own deluge of information, confronting the fragility of digital data and the noise of endless content, their quiet example offers a crucial reminder. Preservation is not a passive act of storage. It is an active, deliberate, and profoundly human choice. It requires us to decide what is precious, to maintain the tools needed to understand it, and to keep the pathways of access open for generations we will never meet. In honoring their past labor, we shape our own future. The light they kept burning through the long night now illuminates our path forward.